So in today's class, we shall be discussing utility theory. Some of you might have come across this topic while studying economics at your school level or at your college level. So first of all, just to begin with, what exactly do we mean by utility? If we want to measure the satisfaction which we get by pursuing any activity, then that is something which we term as utility. Or the way to measure that is something called utils. Again, it is a bit arbitrary in nature. There is no honestly correct way to define what how much satisfaction you are getting it. But if we want to try to do that, then the term which we have for that is utils, or yeah, the utils is the term which we have for it. Now generally, when we talk about, let's say, money, investments and all, our aim is usually to what? Maximize our wealth. If it's a random variable, then a better way would be to say to maximize our expected wealth. Utility theory here in this world, or under this model, we assume that the investors are looking forward to maximizing their utility out of it. Most of the times, higher wealth will be leading to higher utility, but the moment we bring in the concept of randomness, variability over here, then we're not just looking to maximize our expected wealth. Rather, what we're looking at is maximizing our expected utility. So to begin with, first of all, just to give you a background, a more formal background as to what utility is, how do we measure it, so on. Let me share my screen. Do all of you take notes from it, although most of them are directly from material, but to have it in a concise, structured way, do keep taking the notes. So first of all, give the heading, introduction. Utility is the satisfaction that an individual obtains. Utility is the satisfaction that an individual obtains from a particular course of action. Next, give the heading utility function. Utility function. In the application of utility theory to finance and investment choice. In the application of utility theory to finance and investment choice, comma, it is assumed that a numerical value called the utility. In economics, you might probably have done utils only, UTILs. Here they are saying it to be utility itself. It is assumed that a numerical value called the utility can be assigned to each possible value of the investor's wealth, by what is known as a preference function or utility function. After utility function, within brackets, just write UW. This is how we denote a utility function, where W is corresponding to wealth and UW corresponds to the utility associated with that wealth. Next, give the heading expected utility theorem. Expected utility theorem. First point, The expected utility theorem states that a function comma uw comma can be constructed as representing an investor's utility of wealth w comma at some future date. Second point, decisions are made in a manner decisions are made in a manner to maximize the expected value of utility to maximize the expected value of utility given the investor's particular beliefs given the investor's particular beliefs about the probability of different outcomes about the probability of different outcomes. So the first thing which you'll need to understand is, and at times, when we would be doing certain numericals, our intention under this theorem is that an investor is looking to maximize his or her expected utility and not his or her wealth. So this might lead to selection of choices inherently where the expected wealth is not being maximized. It might be the case that it is lower, but it is giving a far higher utility. And this is something which we can intuitively understand as well, depending on the ability for an individual to take risk or the risk averseness. He or she might be willing to let's say satisfy with a small amount of money or a slightly lower amount of money just because it brings a lot more certainty associated with it. A very simple thing is that a lot of us might prefer to let's say work in a stable jobs than to try something of our own, given the inherent risks associated with starting your own enterprise and all. So it might be that you end up let's say earning more money if you have your own business, but yet still a lot of people would prefer to have a stable job, although the amount of money they make there is far lower. So we would be looking at over here in detail. So take down this formula for expected utility. In case we have a discrete function for utility, it will be of this form. And in case we have a continuous utility function, it will be of this form, where PWI is nothing but the probability associated with having a particular amount of wealth, and FW becomes my PDF in case we have a continuous random variable. EU is the expected utility. PWI is the probability, UW is nothing but the utility function, FW is nothing but the PDF in case we have a continuous random variable. So keep in mind, all we're looking at is to maximize this particular term. Take down this question and give it a shot. Yeah. Do take this, all of you do take down this question. Do write it down and then give it a shot as well. First, take down the question. Take the next 5-7 minutes. Then I discuss the solution. Just a minute, guys. Let me just repeat some parts of it because I had stopped recording. So the first part is the investor is investing everything. Sorry, is not investing anything in investment Z. So the $100 remains $100, and therefore the utility will be nothing but log of 100. Part two, investor is entirely investing in investment Z. So the 100 will be either becoming 120 or 82, and therefore the expected utility will be half ln 82 plus half ln of 120, which is coming out to be 4.597. Also, if you just keep in mind, if you take a look at the returns of investment Z, on average you're gonna gain 1%. How I'm getting this 1% is plus 20 minus 18 into half. So on average, I'm getting 1% return, whereas if I'm not investing anything, I'm getting 0% returns. So it might look like any rational investor, should prefer to invest in investment Z, because then that is leading to a higher expected amount of wealth. But if we take a look from the point of view of expected utility, in part one, where we are getting 0% returns, the utility is coming out to be 4.605, whereas in the second case, it's coming out to be 4.597. So therefore, here investor A is actually preferring to not invest in investment Z. As for the third part, a proportion of wealth is being invested in investment Z to maximize the expected utility, and we also need to find the actual, the numerical figure when A is investing a proportion in the investment Z. So the first thing which we are going to do is, a proportion is being invested in investment Z, it implies that the amount which is being invested is 100 A. If plus 20% returns are achieved, then this becomes an amount in investment Z. And in case minus 18% is achieved, then this becomes the amount in the second case. Okay. Show just a second. Yes. In the second case, when minus 18% returns are being achieved, the amount becomes 100A into 0.82. Now, what about the other amount? A proportion is being invested in investment Z. So the remaining amount, the which is 100 into 1 minus A, remains as it is, and the amount of that will remain the same only. So the two scenarios which you get is these two. This is under the first case, which has a probability of half. This also has a probability of half. This is my wealth under two different scenarios. It's always preferable that you start with defining the random variable, because it just makes it more easier. Even in case you make some errors, tracking down these errors becomes more easier. Now you have wealth in two cases. You need to find the expected utility. Now you can obviously simplify the first part, and this will become something like 100 plus 20, and the second will become 100 minus 18A. This is gonna become my wealth, and now my expected utility will be something of this format: half into ln of 100 plus 20A plus half ln of 100 minus 18A. Now we wish to maximize expected utility, so we need to differentiate with respect to A over here. You also need to find the second derivative, and you need to show that it is negative. And then you need to equate first derivative with respect to 0, and using that you need to calculate the value of A. Remember, whenever you're differentiating with respect to one variable only, you always need to show the point of maxima or minima. That is, check the second derivative condition, unless otherwise it's not asked or it's explicitly mentioned, you do not need to do that in the examination. So let me take you through the solution now. So again, in the answer, we'll more often than not just see them coming with the direct step itself, but it's always advisable that you first construct the random variable. Now, once you differentiate, you're getting a particular expression, which is coming out to be minus 9 divided by 100 minus 18A plus 10 divided by 100 plus 20A. And equating this to 0, you're getting A as 0.277, which should be something by 999, 27 by 99, 0.2727. 2.7. This should have a form in a fraction, ideally. 0.77. X is equal to 10x. 27 by 990. Sure. 5 by 80. If you all want, you will be getting A as basically 5 divided by 80. You can leave the answer in the fractional form as well. Because later when you will be calculating the expected utility, depending how you round off A till, whether you round it off till 2 decimal place, 3 decimal place, 4 decimal place, the final answer could vary. So whenever you get it in a fraction form, it's always preferable to use that only. Second derivative they have also shown and it's coming out to be negative. You can simply see that first term has minus 18 into 9, which is minus 162. Second term also has minus 200. Denominator is basically positive only. So without incorporating the value of A as 0.277, you can say that this will always be negative for all real values of A. Therefore, the point of this point is nothing but a point of maxima. And then finally putting this in the equation, we are getting this to be 4.6066. If you all have any doubts in this question, please ask. If not, just let me know by typing a no in the chat box. I'll proceed to the next part. Others, please respond. If you don't have any doubts, please type a no. Okay. Moving forward, next give the heading derivation of expected utility theorem. Derivation of expected utility theorem. So under this, write down the 4 points, or rather start in this way. The expected utility theorem can be derived. The expected utility theorem can be derived from the following four. From the following four axioms, AXIOMS. First one, comparability. Comparability. Second, transitivity. Transitivity. Third one, independence. Fourth, certainty equivalence. certainty equivalence. Now again, the exact derivation as such, it's not here. It's not a mathematical derivation as such. It's more of using these four particular results. So the first one is comparability, which simply states that if you prefer A over to B, and let's say not that actually, sorry, that is for transitory. Comparability is that, let's say if you have two investment choices, A and B, then either you will say that A is better than B, or A is not better than B, or both A and B are indifferent. Apart from this, there cannot be any other scenario. So that is why the term comparability, you can compare any two investment choices. Either one would be better than the other, or both of them will be the same. So that is what they have written over here. In other words, for any two certain outcomes, A and B, either A is preferred to B or B is preferred to A, or the investor is indifferent between A and B. Mathematically speaking, utility A is either greater than utility B or less than utility B or equal to utility of B. Next is transitivity, which simply states that if an investor prefers A over B and let's say B over C, then this would imply that the investor will also prefer A over C. Mathematically speaking, if UA is greater than UB and UB is greater than UC, this should imply that utility of A is greater than utility of C. Again, mathematically, this might sound very obvious. If I just want to take a practical scenario, when you ask a particular child whether you prefer apple or orange, let's say she says she prefers apple, then you ask her whether you prefer orange or papaya, she says she prefers papaya. No, sorry, she says she prefers orange. So now if you ask her whether you prefer apple or papaya, your answer should be as apple. If not, if you're getting papaya, then that is something which is not covered in the particular theorem. So your choices are remaining consistent only. If you prefer A over B and B over C, you would be preferring A over C under all circumstances. And mathematically, again, if UA is equal to UB and UB is equal to UC, then UA is equal to UC. Third one is of independence. This basically states that, again, if there are two certain outcomes, A and B, and suppose that you prefer A over B. Now, whatever combinations you make, let's say you bring another event C, and now you create a gamble out of A and C, and you create a gamble out of B and C with same probabilities. That is, the probability of getting A is same in both of them, and the probability of getting, let's say, not the probability of A, rather, let me word it this way. We start with two certain outcomes, A and B. Say A is preferred over B. Now you let us consider another outcome, C. Now if I take the first scenario where outcome A occurs with probability P and C occurs with probability 1 minus P. Second option, B occurs with probability P, C occurs with probability 1 minus P. In this case, you will still prefer the first option compared to the second option. That is just because of bringing in another choices will not influence the final decision. Mathematically speaking, if UA is equal to UB, say, then P into UA plus 1 minus P into UC is equal to P into UB plus 1 minus P into UC. And if let's say UA was greater than UB, then this particular equation over here, there would be basically a strictly greater than sign over here. That is, if I'm saying, let's say there are two bags, okay. One bag, say you know for sure has 100 rupees note, another bag has 50 rupees note. You are going to prefer what? Selecting first bag. Now I bring in third bag, which might, let's say, have a 200 rupees note. Okay. Now, let's say your eyes have been closed. Okay. In the first case, let's say the probability of you selecting bag A is something and selecting bag C, the last bag, is another probability. Let's say for the time being P and 1 minus P. In the second scenario, you have bag B and bag C. Now you get to choose which combination of bags do you want to select. You will prefer which one, bag A and bag C only, because bag C to is remains the same in both of them. Bag A has 100 rupees, whereas bag B has only 50 rupees. So this is third one. If you want to just sort of understand it intuitively, just because you bring in a third combination and make a gamble out of it, it is not going to make any difference. If you prefer A over B, even if C comes and a gamble is created, you'll prefer the combination of A and C over A and B. Last one, what we have is certainty equivalence, which basically states that, say we have three events or three outcomes where A is preferred to B and B is preferred to C. Now we can create a gamble in such a way so that the expected utility which you get from a gamble which has a payoff of either A or C is equal to the certain case where the outcome B takes place. So if I just want to take a look at it over here, suppose that A is preferred to B and B is preferred to C, then there is a unique probability P such that the investor is indifferent between B, that is a certain outcome, and a gamble giving A with probability P and C with probability 1 minus P. A more mathematical way of saying that is, just take three numbers, okay, where A is less than B is less than C. Now you can express B as nothing but PA plus 1 minus P into C, where my P lies between 0 to 1. It's a very simple thing. If I take, let's say, 2, 3, and 7, I can find such a weight so that 2P plus 7 into 1 minus P will give us nothing but 3 only. So over here, utility B will be nothing but P into utility A plus 1 minus P into utility of C. So what the fourth part is saying, that such a P is going to exist, and the value of which, because it's a probability, it is going to lie between 0 and 1 only. And note that here they have mentioned the order that A is strictly less than B, strictly less than C. So the value of P which I'll be getting will be between 0 to 1. More precisely this and not this. Because if P either takes the value 0 or 1, in this case, now either A will be equal to B or C will be equal to B, which basically nullifies my starting position. So this is just a bit technicality over here. Implication of this over here is that the whole concept of insurance. Let's say you have bought a particular car, you might have some let's say damage to the car in a particular year, or you might not have a damage, right? So if you haven't taken out any insurance, you might not have to pay anything, and in case there is a damage, you might have to pay something. What happens when you purchase an insurance in a very simplistic case, where let's say you purchase an insurance, whatever is the loss, if at all, the insurance company pays for it. So what you're doing is, by paying a fixed amount of premium, you are basically now making things certain. Say you have 100 rupees, premium is 2 rupees. You pay 2 rupees to the insurance company, you're left with how much? 98. Now, whatever happens to the car, you will be left with how much? 98 only. So you're basically transferring from, let's say, what, a gamble. Whenever I mention the term gamble over here, it basically means where the outcome is not certain to a certain nature, in such a way that the utility remains the same only. And using this concept, we will see how we could go about pricing, let's say, the minimum premium which the insurance company should charge, or the maximum premium which the policy holder would be willing to pay. Others, is this concept clear of certainty equivalence? Just type a yes if the concept is clear. I'll move on to the next one. Okay. Next, moving on, give the heading. Non-satiation. Non-satiation. So this is a very simple concept which says that the more you have, the better. That is, you'll never be satisfied as, or let me put it this way. Simply put that the more you get of a particular thing, the better it is. Here, what we're talking about is wealth over here. So write down. It is usually assumed that it is usually assumed that people prefer more wealth to less wealth. Full stop. This is known as the principle of non-satiation. This is known as the principle of non-satiation. Mathematically, it can be expressed as u dash w is strictly greater than 0. See, mathematically, I will make sense out of it. What happens when the first derivative of a function is always 0? What does this imply? The original function is an increasing function. If first derivative of any function is always positive, it implies that the original function is an increasing function. Here w is my variable, so my uw is an increasing function of w. That is, as the value of w increases, uw will keep on increasing, which is what we simply expressed in words. Next, give the heading risk. So under risk now, there are three categories in which we can divide people into with respect to the risk taking ability. One is risk loving, one is risk averse, and the another one is risk neutral. Later on, when we do the other chapters, uh, we would be seeing that in real world, we would assuming, or rather, most of the financial or economic models assume that investors are risk averse. Obviously, in reality, there would be certain individuals or investors who might be risk loving or risk neutral, but most of our models assume that individuals are risk averse. So now, how do I define as whether an individual or an investor is risk averse, risk loving, or risk neutral? We can just take a simple example of a fair gamble and see how their attitude is towards accepting or rejecting that fair gamble. So first take down, we have risk averse under risk, or write it down in this way. Investors can be divided. Investors can be classified into three ways on the basis of their perceivance of risk. First one is risk averse. Second, risk loving slash seeking. And the last one, risk neutral. Now, before getting into the formal definition of same, let me take an example and explain you. So first of all, I mentioned something about a fair gamble. What do I mean by a fair gamble? Where the expected payoff is 0. That is defined as a fair gamble. A very simple example would be, let's say you toss a coin. If it's a head, you earn 1 rupee. If it's a tail, you lose 1 rupee. And it's an unbiased coin. So the expected payoff is what? 1 plus half minus 1 into half, it's 0. You can also take a case wherein you take an unbiased coin, for example, where say probability of head is 80% and probability of tail is 20%. Now, if you get a head, let's say that you get a payoff of how much would it be? Head 4 by 5, 1 by 5. Yeah, let's say if you get a head, you'll be getting a payoff of 1, and if you get a tail, you'll be having to give a payoff of -4. So here also, if you'll take a look at the expected payoff, it's 1 into 0.8 plus -4 into 0.2, which is coming out to be 0. So don't just think a fair gamble is where the both the outcomes have same probability. That is not the case. Expected value should be zero. If both of them have the same probabilities, it implies that the payoffs are also what? Same in magnitude, one being positive, one being negative. Alternatively, it could be that the magnitudes are different and therefore the probabilities will also be different. Now, a risk averse investor is one who will always reject a fair gamble or will not accept a fair gamble. A risk loving person will always accept a fair gamble. A risk neutral person is indifferent. One might accept a gamble, might not accept a gamble, it's indifferent. Another way to put this is a risk averse individual will have to be paid money to accept a fair gamble, or a risk averse individual would be willing to pay money to avoid a fair gamble. A risk neutral person is indifferent. I mean, if offered money, he or she will definitely take the gamble. If asked to pay money to avoid gamble, he or she will never take it. A risk-loving person will be willing to pay money to take a fair gamble. And obviously, if that person is offered money, he or she will obviously be taking the gamble. So to again summarize, a risk-averse person will always reject a fair gamble. We can say this in a way, this person needs to be paid to take that gamble, or this person will be willing to pay to avoid gamble. Risk neutral person is indifferent towards a fair gamble. He or she would be willing to accept it or not accept it. If offered money, definitely will be accepting the gamble. If asked to pay money, will definitely not be accepting the gamble. A risk seeking person will always accept a fair gamble. He or she will be willing to pay money to accept gamble. He or she would be willing to give money. He or she would be willing to pay money to take the gamble, and in case it wants to avoid the gamble, he or she will be looking to receive money to reject the fair gamble. If a risk seeking, you want to take the gamble anyhow. So to stop you from taking gamble, else will have to pay you. Now the whole concept of insurance is on the fact that investors are risk averse, so they'll be willing to pay some amount of money to avoid a fair gamble. Here a gamble could be, whether it's fair or not, it's a different thing. It could be whether the insurer needs to bear some form of loss or not. So now this is one way to look at things. Another way is that a risk averse individual, the amount of utility which this person will be getting by an increasing, let's say, 1 unit of wealth, will be less than the decrease in utility by losing 1 unit of wealth. Means if you will earn 1 rupee, let's say you have an incremental utility of 2. But if you lose 1 rupee, the incremental lose in utility will be, let's say, more than 2. मतलब जितना 1 रुपया जीत के खुशी नहीं होगा उतना 1 रुपया हार के दुख होने वाला है. That is what they are trying to say over here. For a risk-seeking person, it's the opposite. The amount of utility which a increase in wealth will bring of 1 unit is far more than a decrease in the utility by losing 1 unit. And for a risk-neutral person, it's the same. The amount of, let's say, happiness, if I want to use, by winning 1 rupee is same as the amount of sadness by losing 1 rupee. So now take this down. For risk averse, once attending the online class, if you have any doubts, feel free to unmute yourself and ask. Under risk averse, a risk averse investor values an incremental increase. A risk averse investor values an incremental increase in wealth less highly than an incremental decrease in wealth. Full stop. It will always reject. It will reject a fair gamble. It will reject a fair gamble. Acha, now can we just see something? We mentioned for a risk averse, the additional utility which you are going to get for every unit of wealth is actually going to what? Keep on decreasing, right? So can you say something about the shape of the function? When I talk about a risk averse individual, say this person has 100 rupees utility. If this person wins one, the wealth becomes 101. The additional utility which this person is going to get is going to be what? Wait, let me write this down. Say what I'm saying is U101 minus U100 is going to be less than. I'm starting with 100 rupees of wealth. Okay. For a risk averse individual, this investor, if it wins plus one or minus one, the amount of satisfaction which it or the amount of increase in utility over here is going to be less than the decrease over here. That is what we're trying to say. So U101 minus U100 is less than U100 minus U99. From here, can you say something about the shape of the U function? Can you visualize in this way? When we are moving from 99 to 100, we are getting a certain amount of increase in utility. Now, when I move from 100 to 101, this increase in utility is going to be less. When I went from 99 to 100, try to reverse the situation. From 100, let's say utility 100 was 2. Utility 101 is 2.2. Utility 99 is 1.75. When my wealth increased by 1 unit, my utility increased by 0.2. But when my wealth decreased by 1 unit, my utility decreased by 0.25. More than 0.2, that is my point. Can I interpret this as when I went from 99 to 100, my increase in utility was 0.25. When I went from 100 to 101, it was only 0.2. That is, each additional unit of wealth is bringing me less utility. You have all done this. There was a specific term. Law of diminishing marginal utility, right? Which implies what? A convex shape. A convex shape means that the second derivative of function is going to be negative. So, kaha tak did I mention fair gamble? Now it will reject a fair gamble. Mathematically, it implies U double dash W is less than 0. Others, see if you are able to appreciate this in all format, you know, how I went from one thing to another. I could have directly written that the second derivative is negative, but I wanted to show why it is convex. What do we mean by convex? Convex means what? Every additional gain is going to bring us less utility, right? So this is just another way to say that an increase in wealth is the amount of happiness which I get is going to be less than the amount of sadness I'll have if I lose one unit of wealth. Next, for risk loving, a risk loving investor values an incremental increase in wealth more highly than an incremental decrease in wealth. It will always accept a fair gamble. Also, do take down this example as well. This should be helpful to you all to get a mathematical understanding. The one on the screen, this one. So this was under risk averse. Take down this under the risk averse section. Risk loving, I'm not giving example. You can put any values over here and adjust it accordingly. And mathematically, U double dash W is greater than 0. under a risk seeking or a risk loving investor. Also, just to give you a perspective, like I mentioned, that there would be certain cases when expected payoff is positive, yet the investor will prefer to not take that option because he or she is risk averse. Similarly, a person who is risk loving will prefer to take an option where the expected payoff is negative simply because he or she gets more fun by taking risk. Next, risk neutral. हाँ, concave. एक सेकंड, सॉरी, कॉन्वेक्स ये वाला तो, हाँ ये कॉन्वेक्स हुआ ना, कॉन्वेक्स इंक्रीजिंग एट एन इंक्रीजिंग रेट, डिक्रीजिंग एट अ डिक्रीजिंग रेट, हाँ ठीक है, ये कॉन्वेक्स हुआ, कॉन्वेक्स इज ग्रेटर देन 0, हाँ, और ये कॉन्केव है, ठीक है, नहीं एक्स स्क्वायर 2x, हाँ अच्छा कॉन्केव, चलो हाँ हाँ ठीक है ठीक है, ऐसा है तो हम इंक्रीजिंग देख रहे हैं, हाँ कॉन्केव वुड बी समथिंग लाइक दिस डिक्रीजिंग केस में, और इंक्रीजिंग ये तो कॉन्वेक्स है, एक्स स्क्वायर 2x, हाँ ठीक है ठीक है. Next, risk neutral. A risk neutral investor is indifferent between a fair gamble and status quo. Status quo is basically doing nothing. A fair gamble and status quo. Mathematically, U double dash W is equal to 0. Could you all tell me what this implies about the shape of UW function if second derivative is 0?
Straight line 45 degrees.
45, no, second derivative, not first derivative. And 45 degrees when the slope is 1. ठीक है, अच्छा, you are saying slope is 1, so second derivative is 0, fine. You take any straight line, it has a second derivative of 0 only. Second derivative 0 means first derivative has to be constant. If first derivative is constant means slope is constant, it is equivalent to us having a straight line equation. So if you take any equation, any straight line equation of the form uw is equal to aw plus b, first derivative is nothing but a and second derivative is nothing but 0. So write down, such investors have a linear utility function. Such investors have a linear utility function. Full stop. For these investors, maximizing expected utility is equivalent to maximizing expected wealth. For these investors, maximizing expected utility is equivalent to maximizing expected wealth. So how you could use this is, let's say in examination you get a question which has a linear utility function and you have been asked to find, to maximize the expected utility, or which decision should the investor should take under expected utility theorem. वहाँ पे simply, even if you try to maximize the expected wealth, that will result in the decision which would be maximize expecting utility as well. Because of the linear form, both would be maximized at the same point only. Now you could just add in case of a, this is utility, this is wealth. In case of a risk averse person, the utility function looks like this. Increasing because first derivative is positive, which shape? -1. U double dash x greater than 0. लेस देन 0 हाँ तो कॉन्केव शेप हो गया राइट ठीक है एंड दिस इज फॉर अ रिस्क अवर्स दिस इज फॉर अ रिस्क लव वो हम लोग डिक्रीजिंग कर रहे थे तो ऐसे वो सेंस है उसमें एंड फॉर अ risk neutral person the graph would be linear. So the next step which we are going to do is we are going to measure the risk aversion. So it could be that two investors both are risk averse, but they have different magnitudes of aversion towards risk. Similarly, you could also measure risk seekingness, but here since most of the financial and economic models assume that investors are risk averse, we are concerned with measuring what? The degree of risk aversion only. So give the heading measuring risk aversion. Measuring risk aversion. We have primarily two ones. First one, absolute risk aversion. Absolute risk aversion. Within brackets, ARA in capital. Absolute risk aversion. Next one, relative risk aversion. RRA within brackets. For the definition, so they have defined through certainty equivalent first of all. We'll do that later. Give the heading ARA. So this is how I denote absolute risk aversion, and mathematically this is related to utility function in this form. Minus u double dash w divided by u dash w. That is the negative of second derivative divided by the first derivative. And do note that AW will always be positive. Because we are saying it's a risk averse investor, my second derivative is going to be what? Negative only. First derivative is positive, therefore AW is always going to be positive. Next, RW is nothing but W into AW. Now what we are going to look at, how does the absolute risk aversion or relative risk aversion changes as the wealth of an individual increases or decreases. Means, let us just take one case where we are just increasing the wealth. So if wealth increases, does AW increase? Does it decrease or does it remain the same? That is the absolute risk aversion with an increase in wealth. How is it changing? It could be anything depending on the function form. It could be increasing, decreasing, it could be constant. Similar thing we would be doing for the relative risk aversion as well. So this might become a bit tricky. So hear this carefully. Write down this first of all. Investors who have an increasing ARA. Investors who have an increasing ARA hold a decreasing absolute amount of wealth.
Can you repeat, please?
Investors who have an increasing ARA hold a decreasing absolute amount of wealth in risky assets as their wealth increases. As their wealth increases. Now try to picturize this. What I am saying is, if wealth is increasing and if the absolute risk aversion is also increasing, it means what, the person is getting more scarier or more risk averse as wealth is increasing. If a person becomes more risk averse, he or she would be investing less amount. The term here is less absolute amount in riskier assets. So, for example, if initially the person had a wealth of 100 and say this person was investing 20 amount in risky assets, now if the new wealth of the person is 200, then the amount of wealth he or she would be investing will be less than 20. Could be anything, could be 19, 18, 17, 16, could be anything. So let's say it will be 15 over here. Originally, the person had a wealth of W. This is the amount of wealth invested in risky assets. Amount invested in risky assets. When wealth was 100, this was 20. Now, if the wealth has increased, and we are saying that the person has an increasing absolute risk aversion, means he or she will be investing a lower amount in risky assets. So, this becomes 15. Alternatively, you could go with this as well. Originally, the wealth was 100, amount invested in risky assets was 20. Now you have been given that the wealth is 200, amount invested in risky assets is 15. What can you conclude about the absolute risk aversion? It increases as wealth increases. You can also take an example, what happens when wealth decreases. Same logic hai. Sign might keep changing. Yahan pe we are just taking the case when wealth is increasing. Whenever you are confused, exam if they have asked now what happens if wealth decreases, you just take a numerical example ki what happens when wealth increases. From there you can come up that what should happen when wealth decreases. Like here, what can I say? For an investor having a increasing absolute risk aversion, the amount of wealth invested in risky assets increases as wealth decreases. As wealth decreases, amount invested in risky asset increases. Again, absolute amount. Because when we come to relative, we will be looking at proportions. Is this clear to one and all? This is a very important concept. Do mention a yes if it's clear to all of you in chat box. Okay, perfect then. Next, you can take in this format. Below this only, if wealth increases and if the amount invested in risky assets, this is not a standard short form, I have just created it, AIRA, amount invested in risky assets. If this is decreasing, then this implies that ARA is an increasing function, or ARA is basically increasing, which implies that A dash W is positive. AW is absolute risk aversion. I am saying if wealth is increasing, the person is becoming more risk averse. So the first derivative should be what? Positive. This is just measuring a risk averseness. The higher the value, the more risk averse you are. See if this is making sense to all of you. As my wealth increases and if the amount invested in risky assets decreases, it implies that we have an increasing absolute risk aversion, which mathematically implies that A dash W is greater than 0. Next case could be if W is increasing, AIRA is, let's say, increasing, then ARA is decreasing, and it implies that A dash W is negative. Try to read this out in words and see if it makes sense.
If wealth is decreasing, no?
No, here we are just taking wealth increasing case.
Okay.
For understanding, I also always take the reference point when wealth is increasing. Now in examination, if they are saying wealth is decreasing, from here only you can infer, the sign will just be getting opposite. When I say sign means this particular sign, the amount invested in risky assets. So the second one is could be read as wealth increases and if the amount invested in risky assets increases, then we have a decreasing absolute risk aversion, which mathematically implies that A dash W is less than 0. And finally, if wealth increases and the absolute amount invested in risky assets remains the same, minus that is just remains the same, then absolute risk aversion also remains the same, which implies mathematically that A dash W is equal to 0. Notice my emphasis on absolute amount because next when we look at relative, we would be taking the proportion of amount invested, not the actual amount. Next, what I have is relative risk aversion. So here instead everything of absolute things will become what? Relative. So I just take this example. Here originally I had invested how much? 20% of my wealth in risky assets. Now I'm investing 7.5%. So my relative risk aversion is increasing because the proportion which I'm investing is decreasing. Let me take this case 120, 230. If I look at the absolute risk aversion, that is decreasing. Absolute risk aversion is decreasing as wealth increases. Okay, because when wealth is increasing, my this amount is also increasing. But if I take a look at relative risk aversion, originally it was 20%, now it's 15%. So relative risk aversion is increasing. Relative risk aversion is increasing. The lesser you invest in risky assets, higher is your risk aversion. तो ये थोड़ा confusing it might feel, go in an ordered way. And if I take even this case 120 or 240, your absolute risk aversion is decreasing, relative risk aversion is same because both are having 20% invested. So now in this case, if I want to modify this, my aim everywhere, as my wealth increases and if the relative amount invested in risky assets decreases, it implies an increasing relative risk aversion, which corresponds mathematically to R dash W greater than 0. मतलब structure remains same. Relative amount invested, हाँ मतलब R है. Relative amount मतलब I mean proportion only. Absolute amount, absolute relative amount I mean proportion. अब वो कैसे भी you infer it. Or you can say in proportion to their wealth, amount invested in proportion to their wealth. Take this down the statement, एक statement ले लो. Investors who hold an increasing proportion of their wealth in risky assets as their wealth increases. अच्छा एक मिनट, नहीं ये कंसिस्टेंट नहीं है। लास्ट वाला आई रिपीटेड क्या, इन्वेस्टर्स हु होल्ड एन इंक्रीजिंग एआरए होल्ड अ डिक्रीजिंग, ऐसे था ना। तो इसको लिखो ऐसे, इन्वेस्टर्स हु हैव एन इंक्रीजिंग आरआरए, investors who have an increasing RRA hold a decreasing amount of wealth, hold a decreasing amount of wealth, nahi, hold a decreasing amount of risky assets, hold a decreasing amount of risky assets as a proportion of their wealth, risky assets as a proportion of their wealth as their wealth increases. I'm just trying to keep the structure same, दोनों केस में. There are other ways as well to express this. Write a note and mention these risk measures are often referred to as Arrow Pratt, capital A capital P, Arrow ARROW Pratt PRATT, measures of ARA and RRA. मतलब the formula which I've given you for the utility function, these are referred to as Arrow-Pratt measures of ARA and RRA. Arrow-Pratt measures of ARA and RRA. Next, give the heading relation between RRA and ARA. Relation between RRA and ARA. We will take a look at mathematical form and then we'll take an example as well to come up with what happens when one is increasing or decreasing. किससे start करना है? Mathematical way or first taking an example? वो भी mathematical example ही है, बस utility function नहीं है. Example लेके. ठीक है. चलो let me take an example then. Uh, Hundred and 200 is the wealth. These are 5 different scenarios. First one gives the amount invested in risky asset, and this is also giving the amount invested in risky asset when wealth becomes 200. 5 scenarios, and then we are looking at the amount invested in risky asset. Okay. ये example है. Now let us see what happens. First scenario में ARA क्या हो रहा है? What happens to ARA? Absolute risk aversion. Is it increasing or decreasing as wealth increasing? Decreasing. It is decreasing. Decreasing. Amount invested in risky asset is increasing, so my ARA is decreasing as wealth increases. As wealth increases, ARA decreases. ठीक है? RRA, mental maths करके बता दो. What happens to RRA? Initially 20%, then 25%. नहीं, 50 by 200. Scenario 1. 50 by 200, 25%. So we are now allotting a higher percentage. So RRA is also decreasing. Okay. This is happening in scenario 1. Let's take a look at scenario 2. As wealth increases, what happens to ARA? ARA decreases. RRA remains same. Third case, As wealth increases, ARA, RRA increases. So what I'm trying to tell over here is, if ARA is decreasing, RRA can either increase or decrease or remain the same. We cannot say, it depends. ठीक है, अभी तो आप taken mathematical example, you know. Next we'll see from utility function, if ARA is decreasing, we cannot comment about RRA. We'll come to it, the mathematical form. ठीक है, ये हुआ. अच्छा, scenario 4 में what happens in scenario 4? As wealth increases, ARA remains the same, RRA increase. And fifth case, as wealth increases, ARA is decreasing, and ARA is increasing. ARA is increasing and RRA is also increasing. All of you, is it clear what we have done right now? Five scenarios we have taken. My ultimate goal is just to see, you know, if something happens to ARA, what happens to RRA? If something happens to RRA, what could happen to ARA? So are these five scenarios clear to everyone what exactly is happening? Do let me know by typing a yes in the chat box. Okay, so take this down. Now let's look at the mathematical construct. RW is nothing but WAW. Let us differentiate with respect to W both the sides. R dash W. Here I'll be applying what? Basically the chain rule. I'll be getting AW plus W dash, sorry, A dash W. Basic chain rule we have applied. R dash W is AW plus W A dash W. Also keep in mind AW is always positive. If you look at the definition, AW was minus U dash W by U dash W, which is always positive. So now tell me, what can you conclude if A dash W is greater than 0? What can you conclude about R dash W? Wealth. Our whole analysis assumes that wealth is non-negative only. This is positive, A dash W is positive, AW is always positive. So this implies that R dash W is positive. Then next, if A dash W is 0, then this implies what? Again, R dash W is positive. This term is becoming 0. Ye to positive hi AW. So R dash is greater than 0. If A dash W is less than 0, then this is negative, right? this term is negative, this term is positive, it could be either case. And that is what we just saw. We saw three scenarios where ARA was decreasing, but the effect on RRA were different. So here R dash W could be greater than equal to less than 0. That is, we cannot for sure infer about the sign of RRA. What can you say if R dash W is greater than 0? Or let's begin with actually R dash W less than 0. What can you comment about A dash W? If R dash W is negative, LHS negative, this is positive term, W is positive, it implies A dash W has to be negative. What if R dash W is 0? LHS we have a 0 term, right? This is 0. This is positive, so this has to be negative. This implies again. And then final case. What when R dash W is greater than 0? This term is positive, W is positive. This can be anything, negative, positive, 0. Depending on the magnitude, this can be either of them. So the same thing in examination is asked in the form of words. If you have an increasing ERA, what can you say about RRA? You can get an MCQ based question hypothetically. MCQ है नहीं ऐसे, we don't have that in at least IFoA. So this is the result for that. Next, give the heading. Some commonly used utility functions. Some commonly used utility function. Commonly used utility function. Before we start with it, let me just ask you, what happens to an inequality sign when we multiply or divide by a negative number? Inequality sign changes. If A is greater than B, then minus A is less than minus B. ध्यान देना ये चीज, ठीक है? अच्छा. If A is greater than B, ठीक है? And if I tell you that A is negative, and if I divide both sides by A, writing it on screen, all of you give it a shot. If A is greater than B, and I tell you that A is negative, what will happen when you divide both sides by 0? Both sides by A. What will you get?
Both sides by A.
Both sides by A. क्या आएगा? मतलब both sides divide by A तो क्या आएगा? हाँ, 0 कहाँ से?
A by A 0 भी.
A by A 0 और 1. A by A 1, ठीक है? 1 क्या? यहाँ B by A है. Greater than less than क्या?
Greater than.
1 less than A.
1 less than B by A. Yeah, 1 greater than B by A. This is
Greater than B
option
by
1. This is option 2. All of you post it. Which one is correct? Which of these is correct? First one or the second one? That is good. On average, all of you are wrong. ठीक है, 1 ही होगा. ठीक है. अच्छा. Simple way to do this. 5, 9. Example ले लो, -3 is greater than -4. Now if I divide by -3, I will get a 1 over here. I will get a 4/3 over here. 4/3 is greater than 1. तो ये होगा. Logically, again, B sign doesn't matter. We are dividing by what? A. A is negative, my inequality changes. Again, कोई minus कुछ नहीं आ रहा है. A by A, even if you know A is minus, that is gonna remain 1 only. So this is option number 1. The reason why I did this, the moment we'll do a utility function, normally सब confused हो जाएंगे because we will assume that a particular variable is negative, and then when we divide this variable by a negative number, you all forget to reverse the sign of inequality. So first heading under the commonly used utility functions, quadratic utility function. Quadratic utility function. What is the typical form of a quadratic function? AW square, या स्कूल में AX square plus BX plus C, ठीक है, that is the normal form, but here the form which I use, and there is a reason for using this. So few peculiarities which you will see over here, there is no coefficient of W and there is no constant term over here. Reason for that is why there isn't a constant term, because when we use this utility function, say we want to compare, make a comparison, the constant part is gonna, what does the constant part do? It just, if I have a function bx, y equal to bx, ये line है. If I have y equal to a plus bx, just shift, slope remains the same. So when comparing, this constant part will not make any difference at any point of time. If we just want to compare the difference between two things, so your constant term is not required. And if the constant term is not required, instead of using dw square plus ew, or let's say if I started with ax square plus bx plus c, I remove the c part, it isn't required. Why do I need a and a b? I can write this as what? Ax square by b plus x, and this a by b I can write it as say dx square plus d. Point is, the less number of unknowns you have, the better it is. So here, and it will serve our task. Whether you write d or whether you write a by b, it will make no difference when comparing two different things. So this is my general form. It just ensures that we have one unknown over here, which is d. This is the standard way of writing a quadratic utility function. Now, whenever we model a utility function, it needs to satisfy two things for our purpose. A, principle of non-satiation, which implies that first derivative is greater than 0. Second, we are looking at a risk-averse investor, so the second derivative must be negative. So what happens is, some utility functions will be satisfying these two properties for its entire range for any values of wealth. Some of them will not be satisfying for entire value of wealth, plus there would be certain constraints on this d or whatever other forms we have. So first derivative is coming out to be 2dw plus 1. Second derivative 2d. For the investor to be risk averse, then take it down. U dash w should be negative. For an investor to be risk averse, U double dash W should be negative, which implies that D should be less than 0. And for a investor to satisfy the principle of non-satiation, U dash W should be strictly greater than 0, which means that now, 2dw is greater than -1, which implies that dw is greater than -half. We know that d is negative, which implies that w is less than -1/2d. What it means is as long as W is less than minus 1 by 2D, my first derivative will be positive. So this utility function is valid for this interval. Here everyone forgets ki how this is becoming less than, क्योंकि यहाँ तो greater than है, because D is coming out to be negative. So the moment you are multiplying or dividing by a negative number, the inequality sign should reverse. So this utility function can only model as long as wealth lies between the values 0 and minus 1 by 2D. If there is any other wealth, then this utility function cannot be used for a risk-averse, non-satiated investor. We do not model here. We are assuming that W is positive only. Our entire analysis assumes that a person does not have any debt. Negative wealth है नहीं, positive says that.
Yeah, if we are dividing by D, minus sign on the
T, when we are dividing by D, say D is minus 3. So when I'll write, replace D over here, I'll replace the minus 3 only. No? Pehle se if you take minus, then when you are substituting the value of D over here, you need to take 3 only instead of minus 3. Just think you're dividing by a negative number, which is represented by D, so your inequality will change. ये example ले लो वापस से. Minus 3, now I'm dividing by minus 3. यहाँ तो 1 हो गया, ठीक है. अब minus 3 को suppose if I write C, minus 3 by C, you are saying it should be 4 by. तो अब C क्या है? minus 3 है. Minus minus क्या हो जाएगा? प्लस हो जाएगा. नहीं रुको एक सेकंड, क्या हो रहा है? हाँ तो गलत हो जाएगा ना. यहाँ C कितना है? नहीं, C minus 3 है. 1 is less than. नहीं बट हाँ C minus 3 है. मैं किया था, अच्छा यहाँ तो -4 है ना, सॉरी ऊपर माइनस है. हाँ इफ यू आर सेइंग नीचे भी एक और माइनस C ले आओ तो प्लस हो गया ना. ये 4 by C बचा. C क्या -3, तो ये -4/3 आ रहा है, जबकि चाहिए क्या 4/3. एक स्टेप वी आर डिवाइडिंग बाय नेगेटिव नंबर व्हिच इज से D. यहाँ पे we are dividing by negative number which is D, so inequality changes. Now automatically when you substitute D, तो माइनस वैल्यू उसमें आ ही जा रहा है, अलग से माइनस माइनस प्लस नहीं करना है. एंड इफ यू वांट टू डू दैट, तब यू नीड टू बी केयरफुल कि ये D का सिर्फ पॉजिटिव वैल्यू लेना है, क्योंकि नेगेटिव है ऑलरेडी एडजस्टेड, तो वो कंफ्यूज नहीं करने का वैसे. ठीक है, ये हो गया. नाउ वी विल ट्राई टू लुक एट properties of AW and RW in this case. Direct questions आया है, even in this term only April 2022 around 10-12 marks question was from this chapter. ये same utility function था. They had asked to show कि this has a increasing RA and RRA. तो ये करने में easy है, typing करने में it will take you time and you need to show all the steps. तो है easy, but वही कि typing में CM2 में you might face difficulties as in with the amount of time required. So AW will be क्या 2D by 1 plus 2DW. which I can also write as चलो ठीक है रहना एक बार ऐसे. This is AW, then RW will be अच्छा माइनस है ना. AW is minus U double dash, तो minus 2D by 1 plus 2DW, 1 plus 2DW, which can be written as 1 minus 1 by 1 is 2DW. This is AW. RW, I can arrange this in this form. Now A dash W क्यों आएगा? Simple है. Numerator is constant, denominator W, so I will have minus is there, another minus will come, and 2D 4D square 1 plus 2DW whole square, which is always positive. R dash W, see again, had you written in this form, U by V लगाना होता, would have been complex. This differentiating this will be easier. R dash W, if you differentiate here, this will be coming out to be minus 2D by 1 plus 2DW whole square, which is not negative, it is positive because D is negative. D is negative. So a quadratic utility function has an increasing array, and वहीं से you should know one which has an increasing array will have an increasing RRA. If A dash is positive, A dash W positive, increasing array means your less amount invested, so relatively कम होगा. Derivations are part of syllabus, they are still coming in even for online exams, so do practice this. It is suggestible you will practice this on Word, save the template so that if an exam you get it, can copy paste. Technically not allowed, but no way to catch if you will do it, so could use that. So this was the quadratic utility function. Next, logarithmic utility function. Logarithm utility function. Logarithm utility function. This has even a simpler structure. ln W. First derivative is 1 by W. Now clearly this is positive for all positive values of W. So my range, which is very important to mention, this utility function is valid for all non-negative values of wealth, or more technically all positive values of wealth. W0 will be undefined. U dash W is nothing but minus 1 by W square. नहीं, strictly greater than 0. इसमें तो not satisfied. Log 0 is undefined यहाँ पे, तो इसमें नहीं है. बाकी if we want to model a utility function, W can take the value 0.
The quadratic में 0
ले सकते हैं. U dash W will be 1, पॉजिटिव है. सेकंड डेरिवेटिव तो ऐसे ही नेगेटिव है, तो कोई दिक्कत नेगेटिव है ही तो. 2D है, W से फर्क ही नहीं, इंडिपेंडेंट ऑफ W. U dash W minus 1 by W square, this is always negative, so this is always risk averse only. AW minus U double dash W by U dash W, this will come out to be 1 by W, and RW will be nothing but 1. Now if you will see, A dash W is nothing but minus 1 by W square, which is negative, and R dash W is nothing but 0. So we have a decreasing absolute risk aversion and a constant relative risk aversion, and usually in humans this is the tendency which we tend to see. that relatively the proportion which are investing in assets remains same. Although if you think logically, after a point of time, if you have, let's say, a lot of money, you might be willing to invest a higher proportion of your assets. Given you need a set amount for living and all, beyond that, whatever additional money you have, you might be a bit more, let's say, क्या term होता है? A bit more careless with your money, so you'll be willing to take more risk with that amount. So this is regarding the logarithm utility function. Third and the final one is the power utility function. Power utility function. W to the power gamma minus 1. It's not in the power, it's separately minus 1 whole divided by gamma. Now u dash w, and the condition here is this is possible for, again, all values of wealth. Gamma must be less than 1. Why, we will just see. First derivative क्या हो जाएगा? Gamma into w to the power gamma minus 1 divided by gamma. So gamma will cancel. W to the power gamma minus 1. This is normal differentiation of x to the power a minus 1 by a with respect to a. नहीं, with respect to x. So ये क्या होगा? A x to the power a minus 1 by a, which is x to the power a minus 1. Second derivative. Gamma minus 1 w to the power gamma minus 2. W we are saying is always यहाँ पे क्या है? Non-negative. Any positive number raised to any real number is always positive. A positive number raised to any real number is always positive. And we want second derivative to be negative, which implies that gamma must be less than 1. So that is why we have kept the condition here. If we want to model a risk averse, see, I am trying to model risk averse, तभी ये conditions आ रहा है. If you are trying to model risk seeking, you need to apply alternate ways. की first derivative तो positive, second derivative should also be positive. ठीक है ये? AW will be coming out to be minus gamma minus 1 by W. Or alternatively 1 minus gamma by W. And RW will be nothing but 1 minus gamma. Now next page कर लेते हैं. AW is 1 minus gamma by W. So my A dash W will be minus 1 minus gamma by W square, which is nothing but gamma minus 1 by W square. Gamma is less than 1, therefore this implies decreasing relative risk aversion. And R dash W is nothing but 0 only. So do take this now. Now give the next heading, certainty equivalent. Certainty equivalent. Now through a question, we will see how to go about calculating certainty equivalent for a particular gamble. So take down the question. Suppose an unbiased coin is tossed once and a gamble exists and a gamble exists in which an investor receives 1 if it lands head, else loses 1. Full stop. Further assume that UW is equal to root under W, and initial wealth is 10. Determine the certainty equivalent of the combined portfolio and for the
And for
gamble. Two things are here. One is certainty equivalent of the portfolio, combined portfolio. Next is certainty equivalent of the gamble. First thing which I need to do is find the expected utility, which here will be nothing but half root 9 plus half root 11. Initial wealth is 10, so my wealth will either be 11 or 9 with equal probabilities. Unbiased coin is there, so it means probability of head and tail is half only. And this will come out to be 9.975 till 3 decimal places. Now, when I say the certainty equivalent of the combined portfolio, it basically means if you do not have to take the gamble, what certain value of wealth will give you the same utility as this. So this is denoted by basically CW. Utility CW is equal to 9.975. That is root under CW is nothing but 9.975. And from here I will calculate CW, which will be the square of 9.975. Huh? नहीं कुछ गलत कर रहे हैं. ये 9.975 थोड़ी आ रहा है भाई. 9.975 नहीं आ रहा है. 99.75 ये शायद आ रहा है. 9.975 नहीं आ रहा है. अच्छा, दिस इज रॉन्ग. दिस इज नॉट 9.975. ये तो 1.5 प्लस
3.15.
हाँ ऐसा कुछ 3. एंड स्क्वायर नहीं, वो उसका स्क्वायर है, वो CW है. 9.975 CW. CW will come as 9.975. So this CW is being referred to as the certainty equivalent of the portfolio, and certainty equivalent of gamble is defined as CX, formula of which is CW minus W, where W is the initial wealth. So this will come out to be 9.975 minus 10, which is certainty equivalent of the gamble portfolio. Now what CX tells us is, this gives us information how much money the investor is willing to pay to avoid the gamble. Matlab here the investor will be willing to pay as much as 0.025 to avoid the gamble. Kaise you can interpret? The expected utility which the investor is getting by having to take this gamble is 3.1583. The certain amount of wealth which will give the same utility is 9.975. So any amount of wealth which is between 9.975 to 10 will give him or her a higher expected utility than when having to take this particular gamble. So what is the maximum amount which the investor would be willing to pay to avoid this gamble? 0.025. I start with 10. Maximum, even if I give 0.025, I will be left with how much? Minimum 9.975, which will give me a higher utility as compared to when I had to take the particular gamble. So negative value of CX means what? The investor is risk averse, so negative aega, and he or she would be willing to pay money to avoid gamble. In case you get this to be positive ever, means it's a risk seeking investor. Next, do take these statements as well. This is basically giving us a comparison between the value of CX or CW and whether ERA or RRA is increasing or decreasing. So write down, if the absolute value of the certainty equivalent, if the absolute value of the certainty equivalent decreases with increasing wealth, then the investor is said to exhibit declining ERA. And vice versa. Write this as well. The certainty equivalent, next line, the certainty equivalent of the combined portfolio of initial wealth plus gamble is denoted by CW, capital C, small c subscript W, full stop. The certainty equivalent of the gamble is denoted by CX. Next, give the heading variation of utility function with wealth. Variation of utility function with wealth. So now, so far what we were saying that to model the utility function of an investor, we were using a single utility function. But it could be that at different ranges of wealth, the investor would be exhibiting different sort of risk aversion or different sort of risk properties. And so we need different utility functions for different range of wealth. So here, if we just take a look at it, a further extension of the utility function is to consider wealth. It may not be possible to model an investor's behavior over all possible levels of wealth with a single utility function. An obvious example is the quadratic utility function described above. we did that it is valid only for a range of 0 to minus 1 by 2d. Sometimes this problem can be dealt with using utility functions with the same functional form but different parameter over different ranges of wealth. That is, if I using quadratic, say quadratic remains the same, just that say the d part might keep on changing. If you are using power function, it could be that the gamma part is changing according to the ranges of wealth. So under this, what we're going to look at is primarily the state dependent utility function. So what this states is ki with respect to a reference point or a benchmark or a certain point of wealth, above that, the investor will have a different utility function. Below that, the investor will have a different utility function. Let me give you a very, let's say, an example of this. Let's say day-to-day example. You say you borrow 10 rupees from 10 rupees, or let's say 10,000 rupees from your parent. Take care to invest in cryptocurrencies with the promise that you would be definitely returning 10,000 after a month. Now, as long as let's say your benchmark is you need to return 10,000 rupees to your parents, and whatever excess you have, that is your own money, you can enjoy the profits. As long as the value of your cryptocurrency investments are more than 10,000, you might be still willing to take more risk as long as it is more than 10,000, because end of the day you have to return 10,000. Moment it is as soon as it comes nearer 10,000, you will start to becoming a bit more risk averse. If you have 20,000, you might think I can still lose 10,000, right? If you are 15,000, you can lose 5,000, but if you're 10,000, 10, you can only lose 10. So you will start becoming more and more risk averse as you are nearer 10,000. Let's say you drop below 10,000 and your parents have told you if you do not return me exact full 10,000, they will throw you out of the house. So whether you have 9,800 or 2,000, it is the same for you, all or nothing. Either you have minimum 10,000 or anything less than that, you're wrong. So let's say the value of investment becomes 9,900. For you, you have to reach somehow 10,000. So now you will suddenly become extremely risk loving, because by hook or crook you want to reach it to 10,000. So above 10,000, you're behaving in a risk averse way. Below 10,000, you start behaving in a very risk loving way. From a practical consideration of an insurance company, if you will know that most of the insurance company, they take money from you, and most of the times they will be paying you in future only if at all a claim event occurs. So although the insurance company is receiving premiums at outset, even if it is not paying claims today, it needs to pay claims in future whenever it comes. So it needs to keep a certain amount of money so that it is sufficient to pay all future claims. There is something called solvency, that is the amount of money which the insurer needs to keep to ensure it is remaining solvent or not. If an insurer, let's say, is having a total fund value which is slightly more than the minimum amount required for solvency purpose, the insurer would be extremely risk averse, because at no circumstances it wants the value to fall below the minimum solvency level, because there are various repercussions. There might be regulatory action, it might be disallowed to sell new businesses, it might have a bad reputation in front of its policyholders, so on. But let's say once it has breached, let's say the solvency level, then it will become extremely risk seeking, because it will try to regain its solvency at any cost, because the damage has already been done. Now it just wants to ensure it is reaching the level of its solvency. So in such cases, we use basically a state dependent utility function, wherein at the point where the change in behavior is taken, there is a discontinuity. So which can be understood using this graph. This is basically the insurance company, the solvency level, that is the point, right of which, as long as you have a wealth which is more than that, you will be slightly risk averse. Below that, you will see there is a sudden drop of it as well. And if you see the structure also, initially above it is concave in nature, below it is convex. So this is regarding the variation of utility function. Next, give the heading construction of utility function. You can just mention page number 26 and 27. of chapter 2 under variation of utility function. Could refer to that as well. Small topic. Next is construction of utility function. One important thing which might have come in a lot of your mind is we are saying utility function is this, that, okay. How do I come up with this? How do I know somebody is having a log utility function or power utility function, so on? So this is extremely subjective in nature, and most of the times it's not possible to have a precise mathematical formula for saying. So now I am starting with how do we go about constructing the utility function? Which utility function could be used to model the behavior of particular set of investors? One way is you directly question them. If you have this much amount of wealth, what will be your utility? You can plot all different amount of wealths and different amount of utility, and then using certain, let's say, softwares and all, you can come up with a function which satisfies most of them. It is not possible to get a continuous function which will be exactly satisfying them, but using regression or any other techniques, you can come up with a function which closely resembles the actual data points through direct questioning. But obviously, if somebody comes and asks you, if you have, let's say, 1 crore rupees, how much utility do you have? You won't be in a point to answer as such. So direct questioning is something which does not work in real life. Another way is through indirect questioning. So what happens in direct questioning is, let's say we specify the lower range and the upper range of wealth you can possess. Say the lower range is 0 rupees, upper range is 1 crore. And I will say that the lower range, the utility of your wealth at the lower range is 0 and at the upper end is nothing but 1. Now I start with, you are given an option wherein you can either have 0 rupees or 1 crore rupees with equal probability. What amount of fixed money do you need to not take the gamble? What should be the answer? Can you say? Range of it. Again, I'll repeat the question. You are being offered 0 rupees or 1 crore rupees with equal probability, and you're a risk-averse investor. Instead of this gamble, what should be the fixed amount of money that I should offer you so that you forego taking the gamble? Something between
0 to 1 crore, 50 lakhs.
0 to 50 lakhs. It is risk averse. Expected wealth is 50 lakh now. It is risk averse. So 50 lakhs se kami he would be willing to take. He or she might be willing to take 40, 45, 48 lakh. Anything which is less than 50 lakh. 50 lakh to best case है. वो तो करने ही वाला risk averse है. So now you'll be asked this question. You'll have to come up with a figure. Say you say 48 lakh. What it means is that at 48 lakh wealth, your utility is half. At which point at 0 point your utility is denoted as 0. At 1 crore it is 1. At 48 lakh I am saying what? It is equal to nothing but half. Now I will start again with what? You are being offered 0 rupees or 48 lakh rupees. What amount of wealth do you need so that you are indifferent? You say 20 lakh. So at 20 lakh the value of utility function will be 0.25. And similarly you can keep getting it. So this is the example they have outlined as well on similar lines. Suppose that we wish to determine the nature of an individual's utility function over the range of wealth 0 to 4. One possible approach is to fix U0 as 0 and U4 as 1. You can take it to be 0, 100, anything. These are the first 2 points on the individual's utility function. We could then ask the individual to identify the certain level of wealth such that they would be indifferent between W dash for certain and a gamble that yields each of 0 and 4 with equal probability. That is, W dash is the certainty equivalent of the gamble. The expected utility of the gamble is what? Half into U0 plus U4, which is coming to be half. This is from where we are getting half. If you had this in question, when I said utility at 48 lakhs is half. If W dash is 1.8, then we know that U1.8 is equal to 0.5, and thus we have a third point on the utility function. And this set of questioning can be kept repeated. Your next question could be between 0 and 1.8 or also between 1.8 and 4. You can keep repeating this as many data points as you want, and in this way you will have the different points and the different values of utility, and then using certain softwares or any statistical techniques you can fit a particular function. Generally it's a large polynomial. 20-degree, 30-degree order, so on. Matlab ax to the power 30, bx 29, so on. And then they have mentioned the same. We could then repeat the exercise for a gamble involving equal probabilities of producing 1.8 and 4, which yields an expected utility of 0.75, and so on. We keep proceeding. Final paragraph, these processes can be repeated until a sufficient number of points along the individual's utility curve have been identified and plot of those points produced. Ordinary least square regression or maximum likelihood methods can then be used to fit an appropriate functional form to the resulting set of values. So again, if an exam they ask you, they won't ask you the precise function, it is just the layout. I mean, this is the exact framework you need to provide with them. So this was under construction of utility function. Then the last topics we have is, give the heading, maximizing utility through insurance. Maximizing utility through insurance. We might complete in the next 10 minutes only. Under this first point, finding the maximum premium. Finding the maximum premium. So write down the maximum premium, comma, capital P, comma, which an individual will be prepared to pay, which an individual will be prepared to pay in order to insure, INSURE, in order to insure themselves against a random loss, capital X, is given by the equation Let's try to understand what's happening over here. We are looking from the point of view of the policyholder. Initially, I have a wealth of A. If I take out insurance, how much do I need to pay? P, which is the premium. So I'm left with what? A minus P, and then this becomes certain. U A minus P. If I am not taking out insurance, A is the initial level of wealth, X is denoted as loss amount. So what is the amount which I will have? A minus X, and this is a random variable, because the loss amount is going to be random in nature, at least here. So I take the expectation of this and we equate both of them. Using this, we can calculate the value of P. This is the maximum amount of premium I would be willing to pay to get insurance. You might think, why not minimum, why maximum? Any value which is less than this will result in me having what? A higher amount of wealth, which will give me what? Higher level of utility only. So when you think from the point of view of consumer, you need to see how much maximum amount is the consumer willing to pay. When you think from the point of view of supplier, what is the minimum amount at which you would be willing to, provide that particular product. So this becomes the formula. Next, second, finding the minimum premium. Again, when I say maximum premium, it is always from the point of view of the policyholder. When I say minimum premium, it is from the point of view of the insurance company. And say if we see insurance and reinsurance, then we can also find the maximum premium which the insurer would be willing to pay to the reinsurer. Finding the minimum premium. So under this, the minimum insurance premium within brackets, capital Q, the minimum insurance premium within brackets capital Q, which an insurer should be prepared to charge for insurance against a risk for insurance against a risk with potential loss capital Y is given by the solution of the equation if the insurer does not offer insurance, it will have amount A, utility A. If it takes out covers insurance, it will be receiving a premium of Q and it needs to pay a loss of 1. Expectation of this. There are a couple of questions. While reading the material, you can directly practice. Formula remains this only, just need to solve it. Final heading which we have is the limitations of utility theory. We'll just quickly glance through them. So give the heading limitations of utility theory. You can write points are mentioned in material directly. First and the foremost one is to calculate the expected utility, we need to know the precise form of the utility function, which is difficult to get in practice. To calculate expected utility, we need to know the precise form and shape of the individual's utility function. Typically, we do not have such information. Next, even using the questioning techniques described earlier in this chapter, it is still optimistic to assume that it will be possible to construct a utility function that accurately reflects an individual's preferences. So even whatever answers which we are getting, it is still difficult to say whether that is actually accurately capturing all the preferences or not. Second is the theorem cannot be applied separately to each of several sets of risky choices facing an individual. So we can just maybe start with, let's say, 2 at a time, A, B, B, C. If there are A, B, C, D, E, F, we cannot separately apply to each of the several sets. Third, for corporate risk management, it may not be possible to consider a utility function for the firm as though the firm was an individual. So here we are restricting right now to what? Individual investors and all. If we want to apply this to any particular firm who wants to use this for the risk management, then the assumption that we can have a utility function just the way we have for an investor to a firm will not be the correct way to say. And the reason for that is the firm is a coalition of interest groups, each having claims on the firm. They have managers, they have normal employees, they have shareholders, customers, lenders, so on. Each might have their own different choices, so it's not possible to come up with a common set of claims. The decision process must reflect the mechanisms with which these claims are resolved and how this resolution affects the value of the firm. Furthermore, the risk management costs facing a firm may only be one of a number of risky projects affecting the firm's owners. The expected utility theorem is not an efficient mechanism for modeling the interdependence of these sources of risk. And then finally, they are saying that we always tend to assume in most models that investors are rational in nature, they make decision making, assuming they are completely rational, but that is not the case, something which we have practically observed as well. To deal with this, we have a new form of finance, which is behavioral finance, and that is the new thing for the last couple of years and going forward, wherein we are trying to see what causes an investor to make irrational decisions, and then how to kind of overcome it. At a lot of times, we ourselves make certain decisions because we have some bias which we are not able to even realize. So we might end up taking irrational decisions even without being able to acknowledge it. So in the next chapter, which is chapter number 3, we are going to cover behavioral finance only. So this is all we have under utility theory. Any doubts any one of you have, feel free to ask from this particular chapter. If not, just let me know by typing a no in the chat box. I'll conclude the class. Any doubts, anyone? Okay. No doubts then. We'll wrap up the today's class. Thank you everyone.